Okay, so this is the distributions video to go along with the Google Meet that we should have had yesterday. Sorry about the mix-up. I got engrossed with Jacinda and Ashley, so it was more important for me to sit there and listen to how bad this was getting than rush back to do this. So sorry about that. But so what have we done so far? We've talked about continuous distributions, which remember are distributions that are measured. And we've looked at normal, and we've looked at uniform, and we've looked at triangular. Now there's one bit more to do with that, which is called a continuity correction. Which we will talk about once we finish what we're doing at the moment. And then we moved on to our discrete distributions, which are counted. And we did our binomial. And so today we want to talk about our Poisson. And the last thing we need to talk about is expectation. Okay, now, just want to remind you that on your calculator, when you were working out a probability, you were using MCD or inverse normal. When we did our binomial, it was BPD and BCD. And now we're going to go on to Poisson, it's going to be PPD and PCD. So the first letter of all of those is the distribution that you're working with. So therefore, it should come as no surprise when we start using our calculator to work out Poisson in exactly the same way as we have been to do with binomial. Remember, in normal, we don't use the NPD function because it really doesn't make sense. You can't get a single value on a continuous distribution. Or maybe we can, and we might just use it when we get to the continuity correction. We will see. So, remember, our binomial conditions were in situations where we had two outcomes. Each outcome was each outcome had the fixed probability. Each trial was independent, and you had a fixed number of trials. So the Poisson distribution is different because it is for rare events. Okay, so by rare, we're talking about unusual, not very likely. It will have to be expressed as a rate. So therefore there'll be a per or on average, sort of in the sentences, the smallest number of occurrences is 0, and the largest, well, that's the big difference between the Poisson and the binomial. The binomial had a fixed upper limit. In the Poisson, it might be incredibly rare that these things happen, but there is no upper limit. Okay, so those are the main conditions or the main situations in which we get a Poisson distribution. Okay, so we are working with a discrete situation. Events happen, must be discrete, but we are talking about something continuous because it's going to be over an area or over a time. So therefore, that's one of those subtle things that makes this distribution the one we do last, because we can refer to, well, hang on, a normal distribution is like this and a binomial is like that, and this one's a little bit in between, but it's definitely a discrete distribution. Okay, now conditions. Remember, in our binomial, we used pit for our conditions. Okay, this one we're going to use rips for our conditions. So events have to happen at random. Okay, so the randomness is where the R comes from. So events have to happen at random. The second one is events are independent. So I normally talk about the fact that if we think about a rare event, events like earthquakes are rare. They happen at random, and each earthquake, in a sense, is independent of every other earthquake. An earthquake going off in Japan does not mean that we're going to get an earthquake in New Zealand. Okay? So it's important that we keep that in mind. If we're talking about aftershocks, that's slightly different. Just putting it out there. So the next condition is events are proportional to the interval. So let's imagine I was really, really I drink maybe one coffee an hour. It's not a rare event, but Uh, and therefore, if I change that interval from 1 hour to 2 hours, it's reasonable that the number of coffees will have increased as well by the same rate. If I make my day a day, as in 6 hours, then my rate of drinking coffee will increase again. So this is what we're trying to get the idea of, is that the amount that you have is proportional to the time interval that you're working in, or the number of weeds in my garden is proportional to the size of the square that I put on the ground. Yeah, if I make the square 4 times bigger, I should find 4 times the amount of weeds. Okay, and the last one, and it's the one that I'm least happy with. So events cannot happen simultaneously, and that's why I don't like that one, because not having a condition is just as bad. Now, I just want to remind you, I'm not going to go through the formula today because I don't see the point, but the mean is the parameter we're using, okay? And in this, we use an upside down y, which is lambda, Greek letter, okay? And our standard deviation is linked to that. It's in fact the square root of lambda. Okay, so those are the things that we are working with. So I'm basing this on page 38 of the Walker book. Okay, and they've told me the mean number of cyclones per year striking the Pacific Island is 0.6. And I need to work out the probability that there are no cyclones in the next year. So I've got my calculator. To find Poisson, I'm going to go stat, so number 2. I'm going to go distribution, which is F5. Poisson's not on my first screen, so I press F6. Poisson's F1 on my second screen. Right, I am doing a PCD or PPD. Well, no cyclones next year is the probability that X equals 0, so that's a PPD. So I'm going to go to a PPD. So here's my calculator. So PPD. Right, I've got to remember to turn it to variable. It wants to know my X number and my mean. Well, my X number is that there are none, and my mean is 0.6. So therefore, the probability that there are no cyclones next year is 0.5488. Right. Now, when I get to my next one, I said no cyclones in the next 3 years. So that's still the probability of none. So that's still a PPD. But now we've got a change in conditions because my mean was 0.6 per year. Well, now I need to work out my mean for per 3 years. So my mean should be 3 times as big. So now my mean is 1.8. So when I come to work out this one, I've got to have a 1.8 as my mean, and therefore the probability of no cyclones in the next 3 years, well, it was good for 1 year, 55%, but for the next 3 years, it is 0.1653. Okay, everyone happy with that? Right, so the last one is more than 2 cyclones in the next 3 years. So I'm still using my mean of 1.8 per 3 years because I've already worked that out. I now want to work out the probability of X being more than 2. Does more than 2 include 2? No, it does not. So exactly the same as in when I was doing the binomial, I need to turn that round. So I've got 0, 1, 2, 3, 4, 5 going up to infinity. If I want more than 2, I'm looking at this bit. So therefore, I'm going to work out the probability of this bit and take it away from 1. So I'm going to work out 1 minus the probability of X being less than or equal to 2, which makes this whole problem a PCD. So goes back to my calculator, exit. I've got now less than or equal to 2. So that's 1 minus 0.2678, which is, remember the trick, add up each column to make 9, set the last one that adds up to make 10, and there you go. Those are my Poisson-based questions for this. If you can do that, you should be able to do all the pages on page 38 through to page 40 something, okay? And we will reconvene next week to talk about inverse Poisson. Kia kaha, take care guys, survive this lockdown, we'll be fine, and I'll see you back soon. Bye.